Hello, my name is Burak and this video is about regression. How do we solve a regression problem? What kind of strategy do we follow to reach the best possible predictive model? In other words, how do we optimize the solution of a regression problem? This is the part 2 of a two-part series. In the first video, we generated a realistic dataset. We crafted this dataset with a number of real-life challenges. We've gone through quite a few steps to achieve that. So what's unique about this video is the benefit of having generated our own realistic dataset. We are fully aware of the challenges in the data. We can experiment and try different approaches and architectures to unravel how effective they can be for overcoming the challenges in the data. So first video is not a prerequisite for understanding this video. You can start here if you wish, but I do recommend watching the previous video if you haven't already done that. We'll be coding in Python on Google Colab. If you're not familiar with that, it shouldn't be a problem. You can replicate this process in your preferred programming language. Let's move on to Google Colab. I am now screen sharing on Google Colab. Firstly, let's outline the plan, then briefly recap how the data was generated. You'll find a link in the description of this video for this Google Colab file. Also, all of the data is on GitHub, so feel free to make your own copy and have a play. In order to optimize our approach, firstly, we need to detect the root causes of the problems. Problem, in this context, is anything that renders a trained regression model ineffective. In other words, it can't make accurate predictions and you have to improve it before you can deploy it to production. So in simple terms, it doesn't meet your requirements. Most of the time, the root cause of the problem is going to be one or many of these issues. Insufficient sample size, biased sample, too much noise, using wrong algorithm or model. We also need to figure out how can we effectively measure the performance of a trained model. We looked into MSE and RMSE in the previous video, mean squared error and root mean squared error. And in this video, we're going to explore two visualization techniques, Scatterplot and Ordered lineplot. Together, they provide a more comprehensive assessment of the performance. There are many algorithms and models for solving a regression problem. The simplest one is, no doubt, linear regression. We'll cover that in detail. Then, we'll also look into two advanced architectures, random forests and artificial neural networks. These are part of the machine learning or artificial intelligence family. So they are a lot more complex, but potentially a lot more effective. We'll learn how to optimize the application of them. Now, let's recap how we built the dataset. You can skip this part if you already watched the first video. There are 8 predictor variables or x's and 1 response variable or y. Everything is a continuous number. We used a complex function for converting x's into y deterministic, and then added an element of noise to calculate y. So y deterministic is the predictable component of y, and noise is the unpredictable component of y because it cannot be explained by the x's. Take a look at this example. It's a screenshot from the previous video. Noise parameter is set at 10%. So this column will have percentage values between minus 10% and plus 10%. We multiply this column with y deterministic column, and that gives us the noise value. Add noise value to y deterministic in order to calculate y. So what's the observation here? If y deterministic is close to 0, the noise will be close to 0 too. If y deterministic is a larger number, then on average, noise value will be proportional to that. So noise value is a randomized percentage of y deterministic rather than a number generated independently. We have two scenarios outlined here, low noise and high noise. Low noise is the scenario when the parameter is set at 10%, and high noise is based on the scenario when it's set at 50%. You can take a look at the sheet from this link if you'd like to explore further. Let's import the libraries. We'll be using pandas for processing data, Seaborn and Matplotlib for visualization, and scikit-learn and TensorFlow for the algorithms. We'll import more libraries later. And here's the data pulled from GitHub into two data frames. This is how the first data frame looks like. It's for training. As you can see, there are 8 x's and 2 versions of y. One with low noise and one with high noise. 50 rows for the training. The other data frame, same columns, 10,000 rows, and we'll use this data to measure the performance. So we're not allowed to use this data frame for training. Only the first data frame can be used for training. You have to measure the performance of a model on the data the model hasn't seen. That's the rule. And here is the original conversion function, which produced a predictable component of y. As you can see, there are all sorts of relationships: linear, quadratic, logarithmic, conditional, and x8 actually has no relationship. It's irrelevant. It'll be interesting to see if the trained models figure out that x8 is irrelevant. Remember, the objective of the trained model is to mimic this conversion function as closely as possible, because that's the best possible use of the x's. Moving on, here's the list of scenarios in our experiment. We'll train for each of them, calculate the MSE, and visualize their performance. As you can see, there are different algorithms, different sample sizes, different levels of noise in the Y, and also scenarios where there's a bias in the training dataset. Once this experiment is complete, it'll provide very good insight for an optimized strategy for training in general. You may be wondering, how do we get the training data for the enormous noise example or the biased training sample? We haven't covered those yet. I'll explain that later in the video. And here's a function to keep things simple. It takes the scenario information on the table above as the input and outputs the data according to that definition. Splits the x's and y and splits the data for training and performance. And here is a data frame initialization for adding the results as we train for each scenario. So at the end, this data frame will look like the one above with the MSE figures filled. So we have 3 visualization functions. I don't want to go into the detail on their code. You'll see what they produce later in the video. Let's make a start analyzing the data. Always useful thing to do before training a model, isn't it? So here I pulled the data for the scenario with high noise and 50,000 sample size. Let's draw the histogram of the Y. Looks like a skewed bell curve. There's a long tail of marginal values. It's asymmetric. Looks a bit like a gamma distribution to me, if I'm not mistaken. So what's important here is the fact that it's asymmetric and it has a prominent tail. in real life, often it's much more difficult to accurately predict the values in the tail. Most trained models will be good at predicting the center values, but they will struggle at the tail. And here's a real life dilemma. Often being accurate at the tail is more important than being accurate at the center. Imagine this is about the risk of customer leaving or likelihood of a disease. You want to be very good at predicting the extreme values so you can allocate your limited resources the best possible way. Just being accurate here at the center is not that useful. So, to sum up, an excellent model will be equally good at predicting in the tail and in the center. So, let's look at the histograms of the axis. Many of them have gaps in their distribution. And this is by design. You'll know if you watched the first video, we intentionally generated the axis this way because that's generally how real life data looks like. Right, let's do linear regression. Import the regression model from scikit-learn and get the definition of the first scenario from the table. So it's high noise and only 50 data points for training. That's an extremely low sample size, and probably you only have linear regression option if your sample size is that small. More advanced models will not work with 50 rows. And here are the 4 data frames we need for training and then measuring the performance. Also a list for summarizing this scenario for later use in case you're wondering what that is. Training is very simple and very fast for linear regression. Create an instance and call model fit with your training dataset. Now the model is trained, it can make prediction, and here's a prediction for the first row in the performance data frame. So the actual value was 3.7 and the predicted value is 3.1, and the prediction was made using these x's. Not too bad. So I'm calling it training here, but in linear regression what it is doing is based on a deterministic method, finding the best fit line basically. So it's doing something more basic than training in the machine learning context. So let's record the prediction for all rows in the performance data frame. You know, the one with 10,000 data points the model hasn't seen. We are now ready to plot the results and calculate mean squared error. Here are the results. So how should we interpret these results? Firstly, root mean squared error is very high. It's more than half of median or mean actual y. So this is not a very accurate model. So here's the scatter plot on the left. It visualizes a sample of predictions versus the actuals. Remember, it's a sample and it doesn't show all 10,000 predictions here. On the x-axis, you have the predicted y values, and on y-axis, there's the actual y values. Perfect score is when all the dots are on the diagonal line. So let's take a particular dot. So this one is about 4.3 for the actual, and the prediction is about 2.3. So not a very accurate prediction, that one. Dots very close to the diagonal had very similar values for the two. Therefore, they were good predictions. Make sure your scatter plot is a square like this one, not a rectangle for this kind of analysis. Otherwise, it can look misleading. And also don't confuse this with fitted line plot. Also a scatter plot, and you may have seen that on a simple linear regression course. Let me show you one. Here you have an x in one of the axes, and you have a y in the other axis. So it's a different setup, also a scatter plot, but different purpose. Here we have two y's, actual y and prediction y. So let's take a look on the chart on the right hand side. Ordered line plot displays the same information differently. And I prefer this one actually. Here we took the same sample but ordered that sample according to the value of actual y. Then plotted actual y values as a black line against the index. So it goes from small to large values, as you can see. Red line is the corresponding predicted y values for the same indexes. Perfect score here is the two lines perfectly overlapping. So let's take a look at a particular data point. So this particular data point around index 300 had an actual y value of 1.75 maybe, and the predicted y value, which will be on the red line, was about 2.3. So not the best prediction, but not that far off. So what's the observation here for the scenario? Two things. Many dots on the scatter plot are away from the diagonal. Similarly, the red line here on the line plot deviates away from the black line. So on average, predictions are not very accurate. But there is some prediction power. You can see the red line roughly follows the black line here, and dots roughly align with the diagonal, at least for the average values of y. Second observation, model is not good at predicting the extreme values of y. It actually underestimates them. Take a look at this. Any value above 4 is on the one side of the diagonal. Take this particular dot. So actual y value is 10, but prediction is something like 4. So anything above this line is on the one side of the diagonal. And you can see the same problem on the ordered line plot. It stops following the black line once it reaches around 3, 4. To sum up, we have something which may be somewhat useful for average values of y, but it has an underestimation bias for the larger values of y. So let's save the result of this scenario on our table and move on to the next scenario to check if greater sample size will actually improve the results. Okay, I'm going to run that to save the scenario on the table. Here is the next scenario. So same as the first one, but this time we have sample size for training. I consolidated all of the steps above into one cell to speed things up. So let's run that. Here are the results on the table, also on the charts. So smaller RMSE value, that's a good sign. Dots are somewhat closer to the diagonal, and the red line follows the black line a bit better. But I guess it suffers from the same problems as the first scenario. So let's see what happens when we increase the sample size once again, and that's going to be the third scenario. So we have 50,000 sample size this time. Let's run that. So no improvement in the RMSE, almost exactly the same, and visually it's identical to the previous scenario where we had 5,000 sample. So we increased the sample size from 50 to 5,000 and that made an improvement. But from 5,000 to 50,000 we haven't seen any improvement. Park that thought now. We'll revisit that observation later in the video. Let's move on to a different scenario, one with lower noise. So X's can theoretically explain a greater part of Y. I'm going to run it for the fourth scenario now. and take a look at the results. Yes, everything looks significantly better. RMSE much lower. Dots on the diagonal. Red line following the black line much better. And this is not surprising. It's much easier to solve a regression problem with lower noise. The problem is, from the outset, we don't know how much of the mean squared error comes from the noise and how much of it comes from inaccurate approximation of the conversion function. We'll find a way to infer that later in the video. So let's take a look at the next scenario, the fifth scenario. So it's going to be same as this, but with more sample. Let's see if that makes an improvement. So very small, negligible improvement in the RMSE. And visually, it looks more or less identical. So again, increasing the sample size here didn't help a lot. A trained linear regression model constructs a linear equation. It's useful to look at this equation, so let's do that now before we move on to the next scenario. You can find the coefficients and the intercept value using these calls. So here it is, what the trained model thinks should be the conversion function. And here's the actual one I copy-pasted from above. It hasn't done too badly. Take x1. The actual value is 1.85, and it's almost the same number. This is not surprising because x1 relationship with the y is linear, whereas others don't have a linear relationship. So it figured out whether the relationship is a summation or a subtraction quite effectively, as you can see. And for x8, which is, we know, completely irrelevant, it allocated a very small coefficient. So that's not too bad. Moving on, what happens when there's a lot of noise? We have reached that enormous noise scenario now. Firstly, how do we produce the data for this scenario? Remember, noise is the part of y which cannot be explained by the x's. So let's scroll up to find the function which prepares the data. Somewhere here, yes. So if I remove the values of a few useful x's, they become irrelevant. And that's exactly what I've done here. I changed the values of x3, x4, and x6 to half, all values. So these x's become useless in the enormous noise scenario. So let's train for the scenario and see how that looks like now. As you can see, RMSE is very, very high. And if you look at the charts, there is no prediction power here, is there? Nothing useful that I can tell. Red line is almost horizontal. It doesn't follow the black line. And here there is no pattern. Let's increase the sample size to 50,000, and that will be the next scenario, and see if that helps. Right, so we have 50,000 now, but still enormous noise. Right, no improvement in the RMSE, and visually it's the same. So sample size increased, still useless prediction model. Next scenario, the last one for linear regression, is different from what we covered so far. Here, we will have a sample bias in the training dataset. There is no bias in the performance dataset though, only in the training data. and this happens a lot in real life. Your training dataset isn't always representative of the X's that your model will see once the model is deployed. Often, your training dataset is the data from the past, but the performance of your model will be measured on the data from the future, which you don't have, so they may differ. So I'll show you how it's produced. Again, let's scroll up to the function that returns the data and take a look at this line. So we apply a sort against x2 for the training dataset and return the first 5,000 rows. So only the small values of x2 will be in the training sample. So let me visualize that a little bit further maybe. Right. As you can see, the red bars are for the bias sample for x2 and only cover values between 0 and 0.1, whereas for the unbiased sample, x2 covers 0 to 1, much wider. So in the bias sample, in the bias training sample, we have only a subset of the x2 values. So let's train for this bias scenario. Okay, so that's the highest RMSE we have seen so far, and the model doesn't look accurate at all. Looking at the charts, it's obvious this bias caused a massive problem. Most dots are on the one side of the diagonal. Red line often is below the black line. So there is a bit of a trend here, but it's consistently below the black line. So there is a tendency here to underestimate, if you can see that. Bias in the training sample caused an underestimation bias in the performance of the trained model. Again, very common in real life and difficult to solve. And here's the question. What if we try the same sample on random forests or neural networks? Maybe they'll learn how to overcome the issue caused by the bias and perform better. We'll see that later in the video. We have now completed the linear regression part of the experiment. So let's move on to random forests. Random forests are part of the machine learning family, and they are an ensemble learning method. So they are very different from linear regression and also very different from neural networks. It's not going to run as fast as linear regression because it's a lot more advanced and mathematically complex. So starting with importing the model from scikit-learn library, then sourcing the data for scenario number 8. This is the high noise 5,000 sample size scenario. Then training the model similar to what we've done before, and then calling predict for all the data in the performance dataset. We are now ready to produce the results. Before analyzing the results, let's take a look at the performance of linear regression for the same scenario. So it's this row. The value for RMSE was 0.80 in linear regression. Here it's 0.73, so that's better. And visually it looks better too, doesn't it, if you compare the red line to the black line. But there's a problem here. We can't apply random forest the same way we did linear regression. What we've done so far isn't fine-tuned or an optimized application of random forest. We're not really doing justice to random forest. There are 3 considerations. First one, random forests and other machine learning techniques have a random nature. It has that even in the name, doesn't it? They utilize random generators and have randomized initialized states. So if you run them twice, you may not get the same trained model, and sometimes their performance can be very different. So what's the solution for this? We'll train it multiple times and select the best one. But remember, we can only use the training dataset for training, including for selecting the best one. That's still part of the training process. Secondly, hyperparameters. Let me scroll up and show that to you. Here, I have specified a few hyperparameters at the initialization. Hyperparameters change the training behavior of the model in so many different ways, and potentially could make the model much better or worse. We can't really select them arbitrarily like I've done here. We need to try a few different combinations. Lastly, overfitting. This is when the model reaches the point where it gets better at predicting within the training dataset, but worse in the performance dataset. So rather than approximating the overall trend or the conversion function, like this chart, it starts configuring for the training data points and loses the big picture. Very common problem in machine learning, and there are a few techniques to mitigate overfitting. We'll use cross-validation, and that's the most common technique used in conjunction with random forests. Here's an optimized way of applying random forests. We'll import GridsearchCV, which is a very useful tool for both hyperparameter selection and cross-validation. We then initialize GridsearchCV object while specifying a few different values for each hyperparameter. The number of cross-validation folds, and mean squared error for the scoring method. Call fit on the GridsearchCV object and it'll start the training. This will take significantly longer because it's testing every combination of hyperparameters over 5 cross-validation folds. So it's going to train it for 135 times in total. Training is now complete. I can find the model with the best performance using the best estimator method on the GridsearchCV object. Let's take a look at the results. As you can see, that's significantly better than the 0.73 RMSE we saw earlier. So an optimized application produced much better results for the same training data. I saved the results of every scenario on GitHub in case you don't want to run this yourself and instead prefer to spend the time on analyzing the results. You can import them using their scenario index number. So this one is 8. So that is similar to that, but it's not exactly the same because of the random nature of the training, as you know. Let's save the result on our master table and move on to the next scenario. The next scenario is high noise and 50,000 sample size. This will take longer to train. So I trained it in the background. Let's take a look at the results. It doesn't look too bad. Red line following the black line for the most part, and dots closer to diagonal. So let's compare it to the previous scenario where we had 5,000 sample and same level of noise. As you can see, RMSE has improved. So from 0.66 to 0.64. So increasing the sample size from 5,000 to 50,000 actually helped. Unlike in linear regression, in the same two scenarios of linear regression, RMSE stayed the same. Moving on, I want to show you a very useful feature of random forests. They can tell us which X's the model has found to be the most useful. To find that, use feature importances method on the trained model object. So that's ordered from X1 to X8. So it figured out that X8 is the least useful. It has the smallest importance number. And we know from the conversion function that X8 is completely irrelevant. So that's good. Also, it found out that X4 is the most useful. And this is similar to what we have seen in linear regression, isn't it? In linear regression, this was the equation constructed by the trained model. So X4 had the highest coefficient. But this view is going to be more accurate than the linear regressions take. That's because it can figure out non-linear relationships effectively. So one strategy could be to remove your X8 from the training dataset and train again. You can give that a try if you wish. I won't go through the rest of scenarios one by one. Instead, I coded this loop to train for each of them and record the results. It takes about 1 hour to complete all the scenarios. And here's how it looks like once all random forest scenarios are complete. So it's better in most scenarios compared to linear regression for the same data, as expected, but the most surprising scenario is the one with biased training sample. Let's zoom into that. As you can see, the difference between RMSE value of linear regression and random forest is massive. So random forest has made a huge improvement in the training of this dataset. I think it's worthwhile spending some time to explore further. So let's take a look at the charts of this scenario. So that's for linear regression. As you can see, biased data fooled linear regression into a biased model. So it consistently underestimates. But random forests affected to a lesser extent, it seems. As you can see, random forest still has bias, but overall bias is less, and there isn't much bias at the tail, really. It's mostly the central values. Question is, wonder how neural networks will perform on this scenario. We'll see that later in the video. We have now reached neural networks. It's the most successful architecture within the machine learning family, and it can solve some of the most complex problems. Deep learning is a similar term. It's a more specific architecture within neural networks. Majority of AI applications out there, like language translation, image recognition, voice recognition, are all based on neural networks. You may have heard of convolutional neural networks, transformers, LSTMs. They come in many shapes and sizes. They are very configurable. In a regression problem like this one, a basic neural network architecture should be effective enough, such as a fully connected neural network. Multilayer perceptron or a feed-forward artificial network are similar concepts to a fully connected neural network. So let's start with importing a few libraries, then we can discuss the three considerations we mentioned earlier. So these are common problems in machine learning. The same problems exist in neural networks, but the solution to them can be different here. Neural networks take a very long time to train, much longer than random forest, so we need to be mindful of that. For fine-tuning hyperparameters, we'll use a tool designed for this purpose. It's a hyperparameter tuner. For preventing overfitting, we'll use a callback function. We have more control in the training process of neural networks compared to the training process of random forests. So the callback function will monitor the overfitting position proactively and stop the training once it detects overfitting has started. So instead of these two, you can also use GridsearchCV with neural networks if you wish, just like we did in random forests, but GridsearchCV will take a very long time. It's a more brute force approach by trying everything many times, and that is computationally costly. So you'll find a GridsearchCV application with neural networks on this notepad as a bonus section if you'd like to give that a go. Let's start with the first scenario. That's going to be high noise and 5,000 sample size. Sourcing the data for that, and here's how the model looks like. This is the sequential format in Keras library. If you're familiar with PyTorch, it might look different there, but it serves the same purpose. We have two layers with ReLU activation, and we are ending with a single dense layer because this is a regression problem. The loss function is defined as mean squared error, and we also have two callback functions. The first one is to reduce the learning rate once the learning starts to stagnate. The second one is to stop training any further once overfitting starts to cause a problem. This is the one I mentioned before. I'll show you what that does in a minute. And you might be wondering, what are these three lines at the top? They look a bit unusual. So they relate to the hyperparameter tuner we will be using. It's called Keras-tuner, and we imported it earlier. It'll check different values of three different hyperparameters. So for the number of cores in the layers, it's going to check 8, 16, and 32. For the drop rate at the dropout layer, it's going to check 0.1 and 0.25. And for the learning rate, it's going to check those two values. There are other hyperparameters we can fine-tune for, but I think these are the most important ones, so let's keep it narrow. Normally, you would call model.fit to start the training, but because we are using a tuner, we generate an instance of the tuner first and specify how many trials we want. This tuner has a Bayesian optimization mode, which means it's not going to try every combination equally. It will learn from the earlier trials and test some combinations more than the others. It's a good idea. It's a more nuanced approach than grid search. So this line is the equivalent of model.fit. We specify a few more parameters here, such as the batch size, number of epochs, and the validation split. Validation split is very important. It means 20% of the data will not be used in the training, but instead it'll be utilized for checking the performance and overfitting in a proactive fashion while the training is still in progress. The objective is to find the best mean squared error for this 20% subset, and that's what validation loss means here. Okay, let's start the training. As you can see, it monitors the validation loss at every epoch, and once validation loss starts to stagnate, first it will reduce the learning rate, and after a while it will stop the epochs before reaching 100 to stop overfitting. So it reduced the learning rate, there we go, it stopped the epochs before reaching 100 there. Once the training is completed, you can use get best models call with 0 index to return the best performing model. Then calling predict on the performance dataset to produce the predictions. We are now ready to measure the performance. That looks good. Red line, black line alignment, and also dots around the diagonal looking good. And let's see how that compares to random forest for the same sample. So that's random forest, and that's neural network. So lower RMSE score. So we can say neural network has outperformed random forests in this scenario. Here is the loop for training the neural network for the rest of the scenarios. I won't go through them one by one. It takes a couple of hours to run, but remember, I saved the results for each scenario, so you can just import the results from GitHub. And here it is how it looks like once neural network scenarios are populated. I want to move into one particular scenario, that's scenario index number 18. So we have low noise and 50,000 sample size. This is the easiest scenario due to its low noise and high sample size. And let's have a look how well neural network has performed for this scenario. As you can see, a very accurate prediction. So it has almost completely unlocked the conversion function and mimicked that in its algorithm. Near perfect overlap between the red and black lines, and the dots are on the diagonal for the most part. So this is how a very strong prediction looks like visually. We have done linear regression, we have done random forests and neural networks. Now let's calculate the benchmark, in other words, the best model possible. We can only calculate that because we know how y was produced from the x's. We had a conversion function, didn't we? And here it is to remind you. If we apply this function to the performance dataset, that's going to give us the results for the best RMSE value possible. And it differs from one scenario to other, doesn't it? Due to the varying levels of noise or bias. So let's calculate that for the scenario index 1. And that's high noise with no bias. Let's take a look at the results. So that's the best RMSE value possible. For neural networks, it's very close. Random forest, again very close. Linear regression, not that close. Let's take a look at the visuals. If you're wondering why there is this cone shape in the dots as they move away from the zero value of y, remember how we built the noise in the dataset. Noise value was a randomized percentage of y deterministic. So greater the value of y deterministic, the greater the value of noise. And that's how you get this cone shape. So due to the high levels of noise in this training sample, this is the best prediction possible, even in the benchmark scenario. Here's the loop for producing the benchmark results for every scenario. Remember the enormous noise scenario where we messed up the data for 3x's? I built an adjusted version of the conversion function to produce the benchmark for that scenario. Basically added the average contribution of those 3x's as a constant value. It's in the notepad as a bonus section if you'd like to read more. Here it is. And here's the populated table on GitHub. Let's import that and start analyzing the results. Okay, so that's everything. Results of linear regression, random forest, neural network, and the benchmark. Observation 1. Increasing the sample size is generally useful, but not always. Let me show you what I mean. Take a look at this subset. As you can see, linear regression didn't improve from 5,000 to 50,000. So that's the same RMSE value. But random forest neural networks have improved. Advanced models are more likely to make use of more data. Simpler models like linear regression, less so. Actually, neural network almost managed to reach the benchmark result. Compare the two numbers. So maybe if we had 500,000 sample size, it was going to get very close to the benchmark. Observation number 2. Generally speaking, neural networks outperform random forests, and random forests outperform linear regression. However, there are exceptions, and in our experiment, there were 2 exceptions. Observation number 3. For the biased sample size scenario, random forests performed the best by far. Let me show you what I mean. Take a look into this subset. As you can see, random forest achieved a significantly smaller RMSE value than the other two. This could be because it's an ensemble architecture, so it's more resilient to bias. But we can't really generalize that from this experiment only. But generally speaking, ensemble architectures can be more resilient to bias, so it's good to have them in the mix. Observation number 4. For the enormous noise scenario where X's aren't that useful in explaining why, everything has extremely high RMSE value, including the benchmark. Let's take a look at that. Remember, the average Y value was 1.6, so all of these numbers are very high. So neural network is the closest one to the benchmark, but it's still not very useful prediction model. It will have a massive margin of error, so you probably don't want to deploy it to production. Let's summarize the lessons learned from the experiment and come up with a guidance flowchart to follow for improving or optimizing a regression model. Remember, error or mean squared error is made up of 2 things. First one is noise, and this is the part of why X's cannot possibly explain. Secondly, inaccurate or incomplete approximation of the conversion function. And remember, conversion function converts the X's to the predictable part of Y. Okay, assuming you have a couple of thousand worth of training data, the first step for optimization is to train using a number of algorithms or models, like we've done in this experiment. At least one algorithm should be from the ensemble family, like random forest, and at least one from the neural networks. If the improvement is not good enough after that, the next step is to get more data. This is not always easy and it can potentially delay your project, but it's worth it. Train again with a larger sample size and see if it meets your requirements now. Remember, advanced models can get more accurate with greater amount of data. If greater sample size still hasn't solved your problem, you need to investigate bias. What if your training data is not a good representation of the data in production? In other words, training sample is biased. You'll find out if that's the case if the production model has an overestimation or underestimation bias, or if it behaves erratically. That's often a bit too late, and there's some damage, but it can happen. Collect fresh data for training and give it another try. And always consider bias early on in your project and put measures in place to avoid it. Maybe try a small pilot first. So, after the first 3 steps, you're now making the best use of the X's you have. So you're building an accurate conversion function for the X's you're training for. Most of the remaining error is likely to be noise. In other words, what your x's cannot possibly explain. We have seen this in the enormous noise scenario, haven't we? If the noise is too big, there's very little you can do with the data you have. So find new x's that can potentially explain why. That's the only way. It's not always possible and it could take a long time, but that's the only option remaining. Thanks for watching the video and best luck for finding an optimized solution for your regression problem. Thank you.